All right, everyone. Thanks for the introduction, Misha. So my talk will be on the speed limit of a quantum state transfer in a fully connected quantum computer, or more generally, systems with strongly long-range interactions. So before I start, I want to thank my students, especially my graduate student Casey Jameson and Bora, which are actually both here for doing most of the work in this talk. So I want to first give you a motivation of this work. So quantum state transfer is actually a pretty old topic in quantum information processing. So what we are, sorry, it's not. Okay, so what we are thinking about is we have an array of qubits, probably in a lattice, as in a quantum computer or quantum simulator, and we're trying to transfer the state of a qubit A to a remote qubit B here, and we're going to assume that this state of the qubit A is unknown, and all the other qubits are in a product state. Usually, when we are talking about quantum state transfer, we implicitly assume that this only works for some, initial state of the other qubit, of the intermediate qubits, except the qubit A and B. A lot of cases, this state has to be easy to prepare from an experimental point of view. You don't want this state for all the other qubits to be in a huge entangled state. And in this case, a lot of cases, we just assume these intermediate qubits are in state 0, and this has been studied extensively in the system of interacting qubits or interacting spins. But probably more interesting is a quantum state transfer that works unconditionally for any state of the other qubits. And this is sometimes called unconditional quantum state transfer, or universal quantum state transfer, or quantum state transfer without initial state preparation. That basically all means the same thing. We don't actually need to initialize the state. So this just works for any state of the system. And this is actually more similar to a 2-qubit gate, because if you can do a 2-qubit swap gate between A and B, you can certainly do a state transfer between those 2 qubits. And one of the reasons people are interested in quantum state transfer, especially in recent years, is they're directly linked to Lieb-Robinson type bounds. So if you've ever seen a bound like this, which actually try to bound the commutator of an operator that is on side A with a commutator on side B, and where the operator A is evolved in time t. If you're trying to bound the norm of this commutator, which is basically the size of this commutator, by some function that depends on t and r, and this is basically a Lieb-Robinson type bound. This is first discovered by Lieb and Robinson back in 1972 for systems with short-range interaction. In this case, this function on the right-hand side takes this exponential vt minus r, where this v is called the Lieb-Robinson velocity, which is basically proportional to the interaction strength of your lattice Hamiltonian, and r is the distance between the two sides you are looking at. And the reason why quantum state transfer is particularly relevant for these Lieb-Robinson type bound is you actually need this right-hand side of this inequality to be on the order of 1 in order to perform a quantum state transfer, because you are basically transforming information from the side A to B. So any operator on A actually gets transferred to an operator on B, and this commutator becomes non-zero. And we actually consider this Lieb-Robinson type bound to be optimal if we can actually find a quantum state transfer that works to get the right-hand side to 1. Unfortunately, the Lieb-Robinson bound can only bound the speed of conditional quantum state transfer. The reason is simply because the norm we use here is something called the operator norm. So basically, it's taking the expectation value of some operator, I'm assuming Hermitian here for simplicity, and you maximize this value over all the possible state phi here. So this basically means even if the Lieb-Robinson bound is optimal, we can probably only find a quantum state transfer that works for some particular initial state, because we want to maximize this operator norm. And Lieb-Robinson bounds are, of course, important not only for bounding the speed of the quantum state transfer. In this case, we basically know that sending information through a quantum lattice actually has to happen at a finite speed if you have short-range interactions. So this gives you basically emergent light combs. But you can also apply Lieb-Robson bound to many other, problems in many-body physics. You can use it to prove the stability of topological order under local perturbations. You can prove thermalization timescale. You can use it to prove many-body localization in one dimension, or entanglement area law. And there are many other applications of Lieb-Robson bound. So it's a very important a concept that underpins our understanding of quantum many-body physics. And actually, there's a very nice review paper by Andy Lucas group this year. And of course, the main thing of this conference is on systems with long-range interactions. And unfortunately, the original Lieb-Robson bound is only formulated for systems with short-range interactions. But now we have this very nice, broad array of systems where we can engineer long-range, especially these power law decaying interactions. They can be AMO systems, they can be condensed matter systems as well. And for example, we hear a lot of talks on trapped ions where this range of interaction can actually decay with a tunable power law alpha here. And there has been a lot of effort trying to find generalizations of Lieb-Robson bound to these long-range interacting systems. So in general, we can consider Hamiltonians with two-body interactions. You can possibly also extend this to finite body interactions, but for simplicity and also experimental relevance, we're just going to consider two-body interacting Hamiltonians where the strength of this interaction decays as some power law. And also, I'm going to ignore all the single-side terms. It doesn't mean that they're not important, but the fact that you can actually go into the interaction picture of those single-side terms and end up with just the two-body interactions make it possible that we can just ignore those, since they're not going to change this constraint. And finding optimal long-range Lieb-Robson bound has been very challenging and takes many people many years to actually find them. What optimal actually means is that we can actually find a quantum state transfer protocol that saturates the scaling of the time versus distance for the Lieb-Robson bounds. And for these long-range interactions, it has been recently shown that if the alpha, if this exponent alpha is larger than 2 times the dimension plus 1, then actually the system is somewhat close to a short-range interacting system, such as a system with nearest neighbor interactions, in the sense that the time it takes to perform a quantum state transfer, again, I always assume that it's a conditional quantum state transfer if I don't specify it. In this case, it's going to always scale linearly with the distance. And this is very intuitive because at least for nearest neighbor interacting system, you have to do like R sequential swaps to do a state transfer over a distance R. And of course, it's interesting that even for these long-range interacting systems, this is still the case. And what is more interesting is if you actually decrease alpha below 2D plus 1, you start to actually get light cones, or this linear relation actually breaks down. So you actually get polynomial light cones. In this case, you can actually do quantum state transfer in a time that is no longer proportional to distance. This exponent here actually varies between 0 and 1 in this window, and it's actually quite non-trivial to find state transfer protocols that actually saturate this scaling. So you can actually find protocols that can send information this fast. So this takes a lot of effort, and many credits to Alexei and Andy's group in finding those protocols. But the problem is if you further decrease the alpha here, so now alpha is below 2D, we still have bounds and protocols, but the gap of them actually becomes bigger. For example, in this window, the best known Lieb-Robson bound actually shows that the time can be logarithmic in the distance, which is kind of like an exponential speedup compared to the nearest neighbor case. But the best known protocol is at least only a polynomial of this log, so it's not exactly saturated. And things get much worse once you are in this region where the alpha is smaller than D. And this is a region where we call the interaction strongly long range, because it's actually fundamentally different in the sense that the total interaction energy per site actually diverges. But these systems still exist in nature. For example, in this cavity QED or trapped ion systems, you can easily get alpha below the dimension of the system. But then you can see that the best known bounds and the fastest known quantum state transfer protocols, they actually no longer match in the scaling. And to make this simpler, we can look at just the case of alpha equals to 0. And the best known bound actually give you a log n over n, while the best known protocol is only 1 over square root of n. So the gap is about a square root of n in this case, and so they're no longer optimal. If you think this is already a problem, and then for these unconditional quantum state transfer the problem is even bigger. We actually don't understand their speed limit. Largely, we don't understand their speed limit. So first, we don't have optimal bounds on them. But if you think about the fast-known protocol, actually, to my best knowledge, they're actually pretty slow. For example, if alpha is larger than 1, you can pretty much just deal with sequential swaps. You can this is the way you can do a 2-qubit remote gate. And in that case, the time has to be proportional to the distance between the 2 qubits. If alpha is smaller than 1, yes, you can do it faster, but in some trivial way, because you have an interaction that is 1 over r to the alpha between 2 qubits. And in this case, you can just use a direct interaction to mediate a 2-qubit swap gate or additional quantum state transfer. But so in this case, we actually haven't found any non-trivial speed up. So there's like a big question of whether we just need to try harder to find those faster 2-qubit gates with long-range interactions, or that we can actually find better bounds. And this is actually particularly important, for example, for doing quantum computing or doing these quantum error corrections. Like you just heard the talk by Andy. If you can do these non-local gate, fast, especially with power law interactions, it could be hugely helpful in practice. Okay, so the main goal of this talk. So for simplicity, we're just going to focus on the alpha equals to 0 case. So in this case, basically the interactions are all to all. And basically the only constraint is that the interaction strength is smaller than 1. And this can actually be realized by something called a fully connected quantum computer. And this is actually getting pretty popular in quantum computer industry. This is actually a picture from a startup in Europe. This is a startup founded by, I think, by Rainer Blatt and Peter Zoller and others. They're actually trying to use trapped ions to build a quantum computer where each qubit is connected almost with equal weights to the other qubit. So this is kind of like a connectivity graph. And apparently these fully connected quantum computers can be very good at solving certain quantum algorithms, especially where the connectivity actually matters. So once we understand this sort of the simplest case where the interaction is doesn't decay at all, we may be able to generalize this to interactions which decay slowly. So the first goal, of course, is to find the optimal Lie-Robson bound for alpha smaller than d, where I said that the gap is big and we don't really know the optimal Lie-Robson bound in this case. In general, this is a pretty challenging problem, but at least for a subclass of Hamiltonians, especially those that can be mapped to free particles, we can actually find optimal bounds for them. And probably more surprising is that we can actually find exact speed limit for these Hamiltonians for alpha equals to 0. And exact speed limit, or it's like basically a bound that is exactly tight, has never been found in the literature. So this actually requires some very different techniques to do it. The second goal here is, of course, to find speed limit for these unconditional quantum state transfer, or a 2-qubit quantum gate. And in this case, we actually found some new bounds that haven't existed before, and we even have a conjecture that at least for the alpha equals to 0 case, the minimum time to perform a 2-qubit gate is actually just 1. It's on the order of 1. If you can actually prove that, that will be optimal, because apparently we can do that with just the direct interactions. So this is somewhat a surprising result, that even if you have all these extra interactions, you can actually use them to speed up just a 2-qubit gate. You can use it to speed up quantum state transfer, but that only works for some particular initial state. So it's very hard to actually get any speed up for all the states. So that's kind of a very important message here. Okay, so let's first look at the case where we have a free particle quantum state transfer, and in this case we can get optimal Lie-Robson type bound. So this actually is relevant for a lot of quantum state transfer protocols. So we can consider a generic Hamiltonian where we have a global U1 symmetry, which basically means the total sigma z is conserved. And if you do a conditional quantum state transfer where the state of the intermediate qubits is just in 0, then this Hamiltonian just maps to a non-interacting particle Hamiltonian. Actually, it doesn't really matter if these creation and annihilation operators are for bosons and fermions, because there's only one particle that's actually in the state 1. All the other one is in state 0. So it's really a single particle Hamiltonian. And for this case, it's relatively simple to derive a bound that is also a Lie-Robson type bound, which have this form. And if you plug in, So if we plug in the interaction state decay as a power law, we can actually get a speed which is depending on the number of particles n here, especially for alpha equals to 0. N is the only relevant number here because the distance between any two particles is 1. And this is actually optimal because we found explicit protocols that actually have the same scaling. But the prefactors here are actually not tight. It's actually off by at least a factor of pi. So recently what we try to do is to actually sort of tighten up that prefactor. So typically the Lieb-Robson bound cannot provide us an exact minimum time, either for quantum state transfer or just the bound in general. It's always loose by some constant factor. But there has been quite some recent interest in trying to make quantitative improvement for Lieb-Robson bound, even just for short-range interacting systems. In that case, we want to tighten this Lieb-Robson velocity. There's some quite remarkable technical achievement made in these papers to try to tighten up the Lieb-Robson bound just for short-range interacting systems. And there's a motivation of doing that, especially if you want to use this bound as a verification tool for experimental observations, you actually want the bound to be as tight as possible. Because if you violate the bound, you know something is wrong with your experiment. But if the bound is loose, even by a large constant factor, then it's not that useful. But to my best knowledge, these bounds are still not exactly tight. They're still probably off by at least a factor of 2 or 4. But the hope is that since we're only considering a free particle limit, then maybe it's simple enough for us to actually obtain an exact bound, especially for the quantum state transfer here. So the goal is actually pretty simple. Given this Hamiltonian here, and we want to evolve the initial state with a 1 on the source qubit and 0 everywhere else to a state where the 1 now appears in the target qubit. It doesn't really matter where the positions are because the system is fully connected. And we want to find the minimum time. And the only constraint we have is that this hopping strength here, which is coming from the interaction strength, is smaller than 1. So even though this looks simple, it's actually not a simple problem because all these controls, the interactions and the field here are time dependent. And you can actually put arbitrary pulse shapes here. So in general, this is basically an optimization over infinitely many possible Hamiltonians. So fortunately, we've been able to solve this problem, at least to a large extent, using a method from quantum optimal control theory. So this method is called quantum bracket histogram. And this is kind of like a classical analog of this problem. So this is actually first found by the Bernoulli brothers many years ago, many centuries ago. So they consider a classical problem where you are trying to find the shortest time path from the point A to point B based on gravity. And this is actually a non-trivial problem. It turns out the shortest path is not a straight line, it's not a quadratic one, but it's actually a cycloid. And now we can phrase a quantum analog of this problem. So we're thinking about a way to minimize the evolution time for the system to go from an initial state to a target state under a set of constraints denoted by some equations. There's just some functions of the Hamiltonian that is equal to 0. And in this case, we can actually try to solve this problem by solving a particular equation called the quantum bracket-Stone equation. So this is kind of similar to a constraint minimization in calculus, but it's done in a more clever way. So you can introduce this new function f that is kind of like a Lagrange multiplier based on your constraint. And this equation has to be satisfied in order for this Hamiltonian to be time optimal. So if you can actually solve this equation, you basically end up with a smaller subset of Hamiltonians that could be optimal, that could actually minimize the evolution time. So of course, this method usually is only applied to very small systems like single qubit or 2 qubit. And the other constraint is that the constraints here actually must be equalities. And this is not the case for our problem because we actually need, in a lot of these Lieb-Robson type bound, we just require interactions to be bounded by something. So we have to generalize this formally then to incorporate inequality constraint. And the other limitation is that usually you have to, if the Hamiltonian is given by a large matrix, it's actually pretty hard to solve this equation. And in our case, we can actually use an extra permutation symmetry on the intermediate qubits. So this is an extra assumption, but it's kind of reasonable to guess that the optimal Hamiltonian has to be permutation invariant on these intermediate qubits, because all these qubits, they're fully connected. They're not, one is not more special than the other. But this assumption may actually not be necessary if you do a more involved calculation, because given that the Hamiltonian is given by a free particle Hamiltonian, we should be able to analytically solve these equations even if it's n by n matrix. But with this symmetry, we can reduce the Hamiltonian to 3 by 3 and makes it much more manageable. And at the end of the day, the result is actually pretty simple. So the minimum time to perform a quantum state transfer for this Hamiltonian is just given by pi over square root of 2n. And this is actually better than any of the previous found protocols, at least for this type of Hamiltonian. And we can actually identify a family of time optimal Hamiltonians that saturate this speed limit. So this is one of them, and this particular one has actually been found in the quantum state transfer community a while ago, but they've never been able to show that this is actually time optimal. And this also can be experimentally achieved with cavity QED or trapped ions, because you basically just need an RTL interaction among the qubit, and then some magnetic field on the source and the target qubits. And we can also find different Hamiltonians. For example, this one only have couplings between the target source qubit to the other qubit, and in this case, you have a finite strength magnetic field. They all actually fulfill the same perfect state transfer at this minimum time. And we even conjecture that this should be the minimum time even for a general Hamiltonian. Of course, this requires us to prove an optimal Lieb-Robinson bound for the general case. So that's still something we're working at.
Generally not for particle?
Not for particle, but we just don't know any protocol that can do faster than this. Yeah. So this seems to be the global optimum. Yeah. And this is, at least it's exact for the free particle case. Okay, so now I'm going to switch gears to the unconditional quantum state transfer, which apparently to me is actually more interesting because it's at least more useful from a quantum computing point of view. So there's one way that we already know to sort of improve the Lieb-Robinson bound for these cases is that we can actually use the Frobenius norm in this in bounding this commutator. So as I said before, usually in the Lieb-Robinson bound we use the operator norm, which is kind of like the maximum eigenvalue of this operator. And the Frobenius norm is basically like the average eigenvalue. It's actually the root mean square eigenvalue of the operator you are trying to bound. So this is basically the root mean square eigenvalue of O if you're doing the Frobenius norm. In some sense, that is a better bound for this unconditional quantum state transfer, because if you want it to work for any state, initial state phi, then it should work for average state, right? So, and this basically means if you want to do a two-qubit gate or unconditional quantum state transfer, you will need the Frobenius norm of this commutator to actually be on the order of 1. Okay, I also want to mention that there's a lot of growing interest in bounding the Frobenius norm of this commutator, because they're actually related to quantum information scrambling. They're related to dynamics of quantum systems at finite temperature. So they are actually, they have a lot more interesting applications. So in this case, if you take this Hamiltonian, we're looking at, this is like realizable by a fully connected quantum computer, it's actually not hard to bound this with a Frobenius norm. What you're going to get is that the bound depends linearly in time and then also as the square root of n, where n is again the number of qubits in your system. So this seems to suggest that at least we will need a time that is 1 over square root of n to perform the unconditional quantum state transfer. But that kind of coincides with the fastest protocol we know for doing conditional quantum state transfer. So this itself does not rule out the possibility to do an unconditional quantum state transfer as fast as a conditional one, right? So that's a bound we have here. So you would think that maybe we can actually improve this bound to get a tighter constraint, because we actually don't know any unconditional quantum state transfer protocol that can happen in such a fast time. But unfortunately, this bound is pretty much optimal because there actually exist fast scrambling protocols found in Andy Lucas' group again that shows that you can actually make this commutator equals to 1 with a Frobenius norm for a time that is infinitely close to 1 over square root of n with some polynomial, small polynomial overhead here. So this epsilon can be arbitrarily small but finite. So what we actually find is that even though this bound cannot be improved much, the problem is that having this Frobenius norm equal to 1 is actually not sufficient for doing a conditional quantum state transfer or a two-qubit gate. So to understand that, we have to dive a bit deeper into something called the operator growth theory. But the way we can think about this problem is we're looking at an operator that is initially supported on a qubit A, and then we're looking at the time evolution of this operator. We can always expand this in an operator basis. So usually we can choose a Pauli basis. So each of these gamma here can be either X, Y, Z, or identity, because each of these operator can be the Pauli operators and the identity as a complete operator basis. We're also going to assume this operator is normalized, so basically all these coefficients squared add up to 1. Okay, so something we usually do, this is also useful for just deriving Lieb-Robinson bound, is to project this operator at time t into the side B. So this basically tells you how much the operator actually grows to the side B. It kind of characterizes the amount of the support on the side B here. So what you're going to do is to project out the component where this operator basis actually has an identity on the side B. So we are still summing over all the gammas, all these gamma arrays, but the gamma B cannot be identity. So it's only projecting out about a quarter of the component from this big summation here. So if once you do that projection, this part is actually pretty much the same as the commutator. So because you can only get a commutator when this operator actually has a non-identity on the side B, right? If it has an identity on side B, then literally it does not act on the side B, and this commutator will be 0. So basically, so whether this is an operator norm or a Frobenius norm, it requires this to be 1. Requires this projection to actually be 1. I mentioned a little bit about scrambling here. So typically, if you want to get quantum information scrambling, you will need this operator to be supported on basically an extensive number of qubits. So this condition has to hold for about n of the qubits. So that's for scrambling. And now, since we're interested in the 2-qubit gate or unconditional quantum state transfer, we actually have a very different condition. So we actually require this operator A at time t, which is the end of the quantum gate, to be supported only on side A and B. So it cannot actually be supported on any other sides. Otherwise, it's not actually a 2-qubit gate. And from the state transfer language, if it has support on other sides, you can't make it work for any initial state for those other qubits. So this actually means we have to take this projected operator and project again. And here, this P bar here actually denotes the projection that all these intermediate qubits actually have to have identity on them. So except for the qubit A and B, which are our source and target qubit, all the other qubit in this operator basis expansion should be identity. So this is a much bigger projection than this, because this actually will only select about 9 components out of this 4 to the n components here. So most of the component has to vanish, and you only end up with about 9 components here in this projection. So that's a much harder game to play with. This is one of the reasons why it's very hard to get a 2-qubit gate or unconditional quantum state transfer with a speed up. So how are we going to bound this sort of new projected operator? We can sort of have a close look at how this operator can actually grow. And this is something that we typically need to deal with in deriving any Lieb-Robinson type bound. So we can look at how this operator A of t, how this operator A grows in time by just doing a Taylor series expansion. This is just standard quantum mechanics. We can group them by different order, and the case order I denoted by A of k. And then if you project this operator onto the side B, then basically this is made of a bunch of graphs between the nodes A and B with k edges. So I can give you some examples here. So for example, for the first order, which is just a commutator between H and this operator A here, apparently the only term that actually gets you to the side B and also make this commutator non-zero is a term of HAB, right? So I basically draw a line that connects my source qubit A to my target qubit B. So this is the only term that can actually make me grow the operator A to B for the first order. But for the second order, things gets more interesting because now you can introduce another node because you have another commutator here, and this Hij here can choose a different node than A and B. So this green node is basically a free node denoted by L1. So this L1 can actually be any node in the lattice. And as long as this is connected to the target qubit or the source qubit, you will get a non-zero commutator from this expansion. And this game, you can keep playing this game for k equals to 3. Then basically you can introduce another free node from this summation here, and this new node actually can be attached to either one of the first 3 previous nodes. So it's basically you end up with 6 graphs. So if you do this game, you are going to end up with k factorial distinct graphs here. And for each graph, you will basically get k minus 1 free nodes. So if you just try to do a very crude bound on the size of this AK, you can basically see that because I have n qubits in the system, the k minus 1 free nodes is going to give me a power of n to the k minus 1. But I also have k distinct graphs, so it actually scales like this. But unfortunately, this is not going to give you a great bound, because if you just put put this in, you're actually going to get a divergent series, even for t on the order of 1 over n. The main reason is because this k factorial cancels with the k factorial. So you end up with a geometric series that, has a finite convergence radius. So usually the way you solve this type of problem in dealing with conventional Lieb-Robinson bound is you either try to limit the number of different graphs by requiring this new node to only connect to one of the two nodes in the previous edges. And by doing that, you have to add a cost of including some fictitious on-site interactions. And the other way, which is more recently developed, is to try to actually group a bunch of graphs that are actually similar. If they have the same irreducible path from the source to the target qubit, you can group them together and first sum it, which will actually not lead to this problem. But neither of these tricks is actually going to help with our case, because we actually require that the operator to not be supported on all these extra sides. So it can only be supported on the source and the target qubit. So we actually have to keep track of these graphs, at every order. Fortunately, we can actually truncate a lot of these graphs by looking at this more carefully. So again, the requirement is that we only need to consider graphs that actually only support on A and B. So it cannot be acting on all the other qubits. We can actually try to look at this more carefully for a generic Hamiltonian, two-body interacting Hamiltonian, and an arbitrary initial operator here. And the first thing we notice is that for the odd number of orders, we actually only have even-body operators, and vice versa. This is not very hard to realize. So this pretty much means we can treat the odd and even orders separately. But the key observation is the following. So since we want this operator to be only supported on the source and the target qubit, the red and the blue here, actually this should be A and B. Sorry for the typo here. Then the key is that if you want to actually remove a node from the support of this operator, we actually need to at least have 2 repeated edges attached to that node. So this is kind of like from the Pauli algebra here. So if you want, for example, this green node to actually disappear, you actually get identity here. You have to have like a Pauli operator, for example, like a sigma x here and a sigma y here, and another sigma x and a sigma z there. And the sigma x will give you identity, and this is non-commuting. And this is the only way to make this graph actually working. So you actually at least have to have 2 repeated edges for every of those extra nodes. With this, it's not hard to realize that you actually only have k over 2 free nodes instead of k nodes for the order k. And this also means that the number of distinct graphs go down from k factorial to only k over 2 factorial. And that's actually good enough to make the series convergent. Of course, you also need to worry about the order of the graphs, because these graphs are actually ordered because those commutators actually you can't change the order of those nested commutators. But fortunately, you only need to worry about the order of the edge connected to the target node, because all these free nodes, because you're already summing over the entire lattice, the order does not matter. And the source node, the blue node, actually has to be your first edge always. So you only need to worry about the last node, which apparently only gives you an extract of k and doesn't really create a big trouble. So of course, I'm sweeping a lot of derivations under the rug, but at the end of the day, once you sum these truncated graphs, you actually get a bound that is convergent. It gives you a t and then an exponential of n squared of t. So what that means is that it strictly eliminates unconditional quantum state transfer or two-qubit gate at this 1 over square root of n time. Because if you actually plug in the scaling here, you're going to find that this norm is always 1 over square root of n, and it basically goes to 0 in the large n limit. So this basically proves that there's no way you can do an unconditional quantum state transfer as fast as a conditional one. But unfortunately, this is not a huge improvement, because you can also, just make your time a little bit longer as a log n over square root of n, and you can actually still make this 1. But we actually have some ideas of how to improve this. One sort of obvious thing is the reason why we get this log n here is because we get an exponential here. And the exponential is because we have this sum of the series, and we're actually trying to do this in a very crude way by just applying the triangle inequality. And of course, this could constructively add up to an exponential, but we know that this can never happen because the norm of this operator is actually bounded by 1. So this series can never sum to something that is exponentially large. There are actually techniques in deriving this optimal long-range Lieb-Robinson bound that tries to tackle exactly the same problem. We can actually try to use unitarity to somehow constrain this exponential growth. So, in a lot of cases, we can actually show that this is actually e to the I something instead of e to the something. And this will make this term actually at most 1. So if you do that, then at the end of the day, you are just going to get a bound that grows linearly in time. And of course, that means there's actually no speed up that depend on n. If you're not convinced by that, another evidence is that we can consider a generic Hamiltonian with permutation symmetry among all the qubits besides A and B. And in this case, we can actually find that because total S is concerned, we can work on any initial state with total S equals to 0. And if you do a projection onto this subspace, this H of t actually only involves the direct interaction between A and B. So all the other qubits are actually not useful, at least for this particular example. So this is actually a pretty strong evidence that most likely you are not going to get any speed up for doing the two-qubit gate. And okay, so I'm just going to skip the summary here. There's one thing I want to briefly mention. So it seems disappointing that we can't actually speed up two-qubit gate even with these long-range interacting systems. But an alternative way to do this is to actually use qubits. If you have extra levels for your atomic or solid-state systems, you can possibly use that to speed up your two-qubit gate. In that case, we can actually saturate a quantum speed limit bound there. And we have some collaborations with a superconducting qubit experimental group at NIST to do this. All right, so with that, I'm just going to thank you for your attention.
Okay. So can you say more about qubits? I would have expected it wouldn't change any scaling.
So the qubit, the qubit, the scaling is with the d. So the qubit, the d in the qubit. So you can actually get a speed up that is proportional to d, and that saturates some speed limit, and you can actually experimentally do it. Yeah.
So maybe ask. So like all of these considerations, basically, you assume that like you want to make to propagate information from one qubit to another.
Yeah.
But the others, the rest of the qubits basically have to be used like as a buffer or something. So you cannot, for example, like ideally what you would like to do, you would like to make all qubits talk to each other, right?
Yeah. And
you cannot do that, right? You basically have to involve. So how practically relevant are these kind of considerations?
Yeah, I think, especially given that this result that you can't really speed up a two-qubit gate, it probably means even if you have all these interactions, it's better to just do your traditional two-qubit gate. And you can do parallel gates, but it doesn't make sense to use more qubits. The reason why this is, sort of counterintuitive, because at least people have thought a lot about this optimal quantum state transfer protocol. You can actually use this constructed interference with all these other qubits involved to speed it up. But if you want a two-qubit gate, unfortunately, that speed up is probably not there.
Basically, what you are saying, you need, if you want to do non-local stuff, you need some other way to transport quantum.
Yeah, exactly. Yeah.
Thank you for the talk. I was wondering if we can somehow use what you just said to have some intuition on state preparation rather than state transfer.
Yeah, that's a very good question. I kind of listed there because we also have pretty horrible bound for some of these entangled state preparation time, especially when the interactions are long range. Especially if you consider this fully connected quantum computer, we actually only have protocols that can prepare a GHZ state in time 1, where the Lieb-Robinson bound actually tells you it's actually 1 over n or log n over n. So there's a huge gap there. And unfortunately, these, if you want to bound this better, you can't use either Lieb-Robinson bound or this Frobenius norm. So most likely, I think some of the technique we develop, like look at like this more closer look at operator growth, might actually be helpful. So you have to basically invent new techniques beyond Lieb-Robinson bound to do it. Yeah.
All right. You're unlucky because your talk is the only thing which stands between people and lunch. Okay, time for last question. If not, let's thank Zhexuan and all speakers of the